Hello and welcome to this demo on buffer overflows. So there are lots of examples out on the internet on how to do buffer overflows, and what I've done is I've found one done by a guy by the name of Apollo Clark, and you can go check it out on GitHub. It's actually a very good tutorial, and what I'm going to do is walk you through his buffer overflow example step by step. So let's get started. First thing I want to do is look at all the commands. So what are we going to do is first we're going to prep our Kali Linux. Then we're going to create the two executable files. The one is a bash script, the other is a C file. Then we're going to compile them. Then we're going to clean our bash environment. Follow that by, we'll just look at some code. Then we'll run the program normally. Then we'll run the program with a buffer overflow. We'll look at the different registers, the memory addresses we discussed in the theoretical video. Then we'll look at how to take control of the EBP and the EIP using a specific Python script. Then we'll look at the registers again to make sure it happened. And then we'll write an exploit so that we can get a shell command. Great, let's get started and see how this works. Okay, let's get started. So the first thing we're going to do is open a command prompt, bash shell. And there are two files that we are going to use. Let me show them to you quickly. There's envexec.sh and vuln.c. So let's quickly look at envexec.sh. Get env. And as you can see, if you go through the actual script, all it's doing is pretty much cleaning up the bash environment and making an executable so that we can debug our vulnerable C program. And it does this by running the GDP, which is a debugger for the GCC compiler on Kali Linux. Let's just clear the screen again. And let's look at the vulnerable application, because that's actually what we want to see. As you can see, it's a very basic C program. As you can see, it has one function called main, which returns 0. It has declared a character buffer of 500, and we're going to string copy whatever's passed into the main function and into the buffer. So if we pass a string of characters, it will just return the string of characters. But the characters need to be less than or equal to 500 characters. Alright, so that's pretty much it. So in theory, if we put anything over 500, we will get a buffer overflow. So let's quickly get started then. As you can see, I've already compiled the vulnerable application. So if I do an ls, you'll see there it is the vuln. But if you haven't done it already, this is the actual command to do it. gcc -z exec stack, no stack protector, because we're trying to make sure that we get a buffer overflow. Preferred stack boundary is 2, and we're going to use vulnc as the source file and vuln as the executable file, and that's pretty much what I've done there. Okay, so let's start with the executable now and open up the debugger. And you do that by running this command, envexec.sh, which is that batch script, and -d for the file name vuln. Great, so there we go, we're ready to go. So now let's just go look at the assembly code. So there's quite a few commands in GDB that you can look at. This S main is pretty much the assembly dump, and this pretty much shows you exactly what the application is doing in assembly code. So if you're really interested, you can go look up all these different commands and see exactly how it's moving things in memory, but that's beyond the scope of this specific video. Great. So now what we're going to do is we're actually going to run vuln by typing the word run, and we're going to pass it a parameter called hello, which is a 5-character string. So in theory, it shouldn't throw an error, because if you recall, our buffer is 500 characters. And there we go. No, everything exited normally. As you can see, it says exited normally over there. Now we're going to run it and give it a character string of 508, and we do that with this command here. So basically what we're doing in this command is we're going to run a Python script that's going to print the hexadecimal value of x41 508 times. So hexadecimal x41 is the capital letter A, and as you recall, the buffer is 500. Now we're going to write 508. So the last 8 are going to actually overflow the buffer. So we should get an error when we run this code. Let's see. And there we go. As you can see, there's a segmentation fault, and it's telling us that 414041 is in error state. In other words, it's overwritten the buffer and it's gone to a place that it shouldn't be, and it's actually given us the exact value. And if you can see, there's x41, there's x41 there. Alright, so let's look at the different registers now. And we do that with the command info registers. Okay, so as you can see, here are all our registers. If you recall, there's our EBP. As you can see, it's x41, x41, x41. There's our EIP, our instruction pointer, which is the one we're trying to overwrite. And as you can see, that's also x41, 41. So we've overwritten the EIP with our buffer overflow of 8 characters. Great. Let's look at the memory. This is actually quite a cool feature. So if you go x/200x, open bracket, $ESP minus 550. In other words, show me the memory from ESP back 550 times. And if I run that, you can see that's what the memory address looks like. So if I just scroll up slightly for you, you can see we start writing 4141 from about there and literally all the way through. So this is our buffer, and then as you can see, it pretty much ends over there at 41 41 41. Great. So now we can see how our actual buffer is being filled with characters from our Python script, which is excellent. Okay, let's just close that. Now we're going to take control of the EBP. So basically, when we want to run a buffer overflow, we want to know exactly which characters are being written by the EBP. And this script here that I'm going to copy now does that. So, and I'll show you exactly what all of it means as soon as I've copied it. So let's just paste that. Okay, so what we're doing is we're running a Python script. We're going to print x90, which is the null pointer, 426 times. Then we're going to fill the buffer with this code here, which is basically a shell command. It's basically the hexadecimal for running a shell, in other words, running another terminal. And then we're going to add 51, 51, 51, 51 at the end of that, because this is actually what we want our EBP to be. Because what we want to do is we want to overwrite our EIP and EBP with a memory address so that we can actually tell our CPU to go back and actually execute this code, because currently it's just going to print it out. But when we do the buffer overflow, we want this exact address here to be a memory address so that we can trick the CPU into going back into the buffer and executing our code. Okay, so let's just run that and see what happens. As you can see, it wants us to start from the beginning again. And as you can see, I've got a segmentation fault, and now I'm getting that 51, 51, 51. If I now look at the registers, you can see that my EIP is 51, 51, 51, and my EBP is 51, 51, 51. And that's exactly what we're looking for. So if we look at our memory address, which is that command there, you can see we start writing with 9090 over here, and these are all null characters. And then here is our exploit being written into memory. And then finally here is our EBP and EIP, and this is exactly what we want to try and achieve here. What we want to do is change these 51s to one of these memory addresses, so that when the program hits the EIP and says, okay, go to this memory address, it'll be looped back into this memory address, it'll hit a null pointer, and a null pointer will then just pretty much pass it on until it hits a piece of code that it can execute, or a piece of memory that it can understand. And that's what they call a NOP sled, N-O-P, for null pointer sled. So we're going to slide the memory pointer until it hits code, and then it's going to execute that code for us. Okay, so if I look at the actual exploit now, and that's, the code is slightly different, so let's just copy that and then I'll walk you through it. Copy that and paste that. So what we've done here is, at the end here, we've actually given it a memory address, and the memory address is, you have to read it backwards, FBFF So if you go in here, it's AFA, so we're actually giving it this memory address. So we're going to actually tell our pointer, we're going to fill the buffer, then we're going to put our code in, and then when we get to this 5151, we're actually going to redirect it back here to the AFA, and that's going to slide it along, and then it's going to hit this code, and it's actually going to execute that code because it's been run by the EIP. So when we run that from the beginning, there we go. Now we have a Kali prompt, so that now we can actually run commands because we've overflowed the buffer and we've actually executed code. So say, who am I? I'm the root, print working directory, root bf, cat. That's one thing you need to remember when doing this. There is no actual backspace, so you can't make an error. So cat /etc /PAWSWD, and they are all the password hashes. So I hope this sort of tries to remove the mystery of buffer overflows, because I know it can be very overwhelming. It takes a little bit of time to actually get into your head, but once you've practiced it a few times, it actually starts making sense. Thank you very much for watching this video.